Hello and welcome to the very first of my videos of solutions to AS questions. And the AS question that I've chosen for us to study together today is from January 2009, and we're going for an electricity question. So let's get going. Here we have it. I've gone for question 7 in this paper. It says the circuit figure 7.1 contains 5 10 ohm resistors connected to a 6-volt battery as shown. So there's our 6 volts. There's 1, 2, 3, 4, 5 resistors, and our question is to calculate the total resistance of the network between the points X and Y. So we're just interested actually in the ones at the bottom here. So there's X, there's Y. So to find the equivalent resistance here. Now, for this question we have to remember our resistors in series compared to our resistors in parallel. So if they're in series, we simply just add them together. So our top branch can be replaced with 20 ohm resistor, and the same with our bottom branch, 20 ohm resistor. Now, to find the total resistance though of this combination, now we have to use 1 over RT is equal to 1 over R1 plus 1 over R2. So we've got 1 over 20 plus 1 over 20, and that's 2 over 20, and of course then we've got to flip the fraction to get our total, so it's 20 over 2, and our answer then is 10. So 10 ohms. Okay, next up we're going to do the second part, and it says to, let me just scroll this down a bit. There we go. It says use your answer to A part I to calculate the total current drawn from the battery. So we want to find the total current that would go around this circuit. So we find out this resistance. We can't forget this resistance over here because this is going to affect how the current behaves. So we find this is 10 and this is 10. So we simply just have to add those two together again because it's a series circuit. So your answer part there. So our total resistance then this time is 10 plus the 10, so that's 20, and our voltage is 6. So we're going to use the equation V equals IR, put the 6 in, put the R in as 20, and our I is then going to be 6 over 20, which equals 0.3. Part 2 of this question then asks us to work out the current in one of the branches, and it's I1. So hence the term the current in I1. If the total current is 0.3, then find out the current in I1. So let's just have a quick look again at the circuit, and let me just point out to you where I1 is. There's there. So we know that the current coming through here is 0.3. A little bit of knowledge, background knowledge, is that whenever the current gets to a junction, that it splits. Right? It splits with regards to how much resistance there is in each of the branches. And in this case, very simple, the resistance is the same, so the current must split evenly. So we've got 0.3 coming around here, so it must be 0.15, half of that, to work out what the current is in I1. So it's the 0.3 divided by 2, which is 0.15. I'm going to turn the page here and go to page 19, and part B of this question. So this is what it says: explain why the potential difference between points B and C is 0. So let's have a wee look at the circuit again, and there's point B, there's point C. So why is the potential difference between B and C 0? Well, when you think about how the energy in the circuit this time behaves, we looked at the current and the resistance previous there. We're now thinking of the energy. So the coulombs, they pick up their energy from here, they make their way through the circuit, they lose some of their energy here, and whenever they come up here, they lose some of it again, and they get to point B. Now, if they had chosen to go down into the second branch, they would have lost the same amount of energy as they would have if they'd gone up into the top branch. So, the electrical potential energy they have here, they give some of it to the first resistor, and they give some to the second resistor, which is identical to the resistance and the energy they would have given to the second resistor down here. So, let's go to this question again. Explain why the potential difference between points B and C is 0. Because the electrical potential energy lost in the top branch my handwriting's awful, is the same as the bottom branch. There we go. So let's move on to part 2 of B, and we're asked, we're told even, a wire of negligible resistance that's now placed to connect the points B and C of the circuit. The potential difference between points B and C remains 0. So how does the current now drawn from the battery compare with that, well, before the wires connected between B and C? Indicate your answer with a tick. So current is greater, current is the same, or current is less. They also want us to explain our answer. So, if there was a wire went across here, how is the current going to behave differently? Now it says it has negligible resistance. So as the current comes around here, let's take the bottom path, and let's pretend there's a wire up there, and it takes it up there. It's going to have to go through this 10 ohm resistor to get to Y. Now if it didn't go up to there, it would just pass straight through, and that would be, well, it would be the same resistance that it would have to deal with. The same with if it was to take the top path, if it was to go through here or to go down here, so there's no difference to the path that the current has to take. In fact, there would be no current at all that would go through BC. It would all just go through the top or the bottom branch. So let's just write a wee explanation in here. Current stays the same. And explain your answer. Well, it's because no current will flow through BC. Okay, now the last question says the wire in B part 2 is removed from BC and is now placed to connect points X and Y in the circuit. Calculate the current now drawn from the battery in 6 volt from the 6 volt battery. Alright, so here we have our circuit, and we're putting in a wire across here. And in fact, all of the current is now going to go through this wire. Current prefers a path of least resistance, so it's not going to go up there or down there, it's going to go straight through. So the only resistance that we have is this 10 ohm and the 6 volt supply. So those are the two pieces of information we need to finish this. So our resistance is 10 ohms, our voltage is 6, and we're going to use our V equals IR again, and this time is 6 is equal to I times 10. I equals 6 divided by 10, so 0.6. There we go, that's it done. Let's have a wee quick bridle at the mark scheme, see how we got on. So